Okay, so in this video we'll show that a multivariable function that's differentiable is continuous. So let's start off by reminding ourselves what it means for a function to be continuous. So to be continuous, we want to show that for all epsilon greater than 0, there exists a delta greater than 0, such that if absolute value of x minus y is less than delta, then the absolute value of f of x minus f of y is less than epsilon. So if the inputs are close together, we want the outputs to be close together. Okay, so to do this, we kind of want to do a, so if you see the, you're about to see the definition of I know it's not very, it's kind of messy, but we have x plus v, and it would be nice if we could turn this into an x and a y. So we're going to turn the x plus v by substituting into a y, and so that would mean x plus v equals y, and then we could solve for v as x minus y, and then the exact order doesn't particularly matter. So we want to, so this is a continuous, and we're going to suppose differentiability. So we suppose that you know, there exists a d x f, so it's differentiable at a point, and then we're going to show it's continuous at that same point. So this exists, a linear map, and then it satisfies f of, and this is we want to be f of x or f of y. It doesn't matter, but let's say y. It doesn't really matter because it's absolute value. You can switch it around. It's no problem. This is equal to f of x plus, so this is a derivative at x of the function f, and then we want v, but this y we said was x plus v, so v is y minus x, and then we have plus rx of f of y minus x. Okay, and so remember, so we want to show that this is given some epsilon, this difference is less than epsilon. So let's actually first of all just suppose this is start it off, given epsilon greater than 0, and then we do the trick where we say choose delta equal to or such that, and then we leave it blank for a minute, and then we just have a look. So we just go like absolute value of f of y, and then we say that then if absolute value of x minus y, or y minus x, it doesn't matter, this is y minus x because I kind of switched it around by accident, it's less than delta then, I know the opposite then too many times, but it doesn't matter. So it's not English, it's maths. And so then absolute value of f of x minus f of y. Okay, well this, by the definition of the derivative, we can, because it's differentiable, we can write it like this. We can write it like absolute value of derivative of f of x, y minus x, and plus r of x f y minus x. Okay, and so now, because it's what do you call it? It's in the absolute values. You can use the triangle inequality, and we get that this entire sum here is less than or equal to the sum of its parts. So x y minus x, like that. So far pretty straightforward. Over here we're going to use, so we have this as a linear map, and we know that, I mean, we might not know, but we can use the fact that linear maps can be represented by matrices, and matrices have an operator norm. So the operator norm, well, it's not important what it is, but it's like it tells you the maximum value that it can take. And then, so given a vector on the unit circle, there's going to be, it's going to map the unit circle. The linear map's going to stretch out the unit circle, and there's going to be, and it's going to stretch it out into an oval. It's not going to stretch out anything into like infinity. It might stretch it into a line, but it will stretch it into some kind of ball, and the ball will be bounded, right? And then so because it's bounded, that it's going to have a maximum value that we can work out, and this maximum value is the operator norm. So we have this is bounded above by the operator norm of and then the operator norm, and then operator norm is only for the unit circle, and so we have to multiply by the size of y minus x, like that. And then for r of f of x, and this is where we need to look at choosing the delta, right? So from the definition of the derivative, we know that we can make this some epsilon times y minus x for sufficiently small. So what we're going to do is choose x such that so maybe such that r of f of v or something, anything, is less than or equal to epsilon times so its absolute value. For v less than absolute value of v less than delta. Okay, and so let's have a look. So absolute value of v less than delta, and this is less than delta over here, right? And so what we have, it's already satisfied, right? And so we can just say delta, so epsilon, absolute value of y minus x. So it might have been more helpful if I put y minus x here, but v and y minus x are pretty much the same. We just use the substitution just for this proof. And so now we can kind of factor out this y minus x, right? And so I don't have to write it again. I might just scribble this out, put the brackets here like that. Okay, and what we have, or we're almost done, what we have is we have, this is delta right here because it says less than delta, so we can have a less than absolute value of, and this is just some constant, okay, some constant plus epsilon times delta. And so the point is we can make this as small as we like, right? Right, so yes, that's right. So if we make y very close to x, in fact, we do actually, this is better. Let's keep it like that. If we make y very close to x, then we see that f of y is very close to f of x. So what that gives us is, it gives us injectivity. And so if y and x are equal, then f of x and f of y are equal. But more than that, it gives us continuity. Okay, because if y is very close to x, then we have that f of x is very close to f of y, and this is positive, obviously. Okay, and so we're done. So this gives us continuity right there, and so that's the proof. I hope that makes sense. And yeah, so I think I got the proof for injectivity and the continuity at the same time. So I think I got myself a bit confused, but this is correct. So this is the inequality you'll get. And maybe the thing is, with these kind of proofs, I think it's best that you go over it yourself. Just try and see if it makes sense. And so that's it. I'll see you in the next one.